Hi, I'm Vedang. We organized this lecture with Max and Sasha, who are sitting right in front of me right now. They're the people in the nice pink ties and pink hair. And our friends from Studium Generale are back there, so you can say hi to them later or now. So this lecture was this idea of this foundation was to sort of bring physics and bring science to, well, everyone, and to sort of take it out of this fear of science that it's done behind closed doors by people we don't know, and then every now and then we hear something that doesn't make a lot of sense. So we're going to try to make some sense of that today. And we're going to today hear about cleverly shaped stellarators, which are a promising step in nuclear fusion. And to talk to us about that, we have Josefine Proll from Eindhoven. She's an assistant professor there, and she's from Germany. She did her PhD at the Max Planck Institute. Before you ask me which one, it's Max Planck Institute for Plasma Physics in Greifswald, I guess. Yeah, and yeah, I'll hand over to her. And up you go.
Thank you so much for having me here. Thank you so much, guys, for inviting me. Thank you to the family of Hendrik de Waard. It's such a pleasure and such an honor to be here. As Vedang said, I'm from Eindhoven University. And I don't know whether you know, but it's a fairly new university, so I'm slightly intimidated by the room and the splendor. So also I'm slightly worried that I'm kind of driving off with the little cart. So let's see how that goes. Before we start, I've always wanted to do nuclear fusion. Since I was 13, I kind of visited the Max Planck Institute as a slightly geeky child, and then I thought, ooh, we might be able to save the world with nuclear fusion, and then I knew I wanted to get into it, and here I am, so I'm really quite lucky. So I hope I can transmit this joy and the excitement about nuclear fusion to you somewhat. Before we really get into it, I want to kind of know who of you here has some sort of background in physics. Can you raise your hand? Oh, that's a lot. That's a lot of people. Nice. Okay, all right. And now those of you who feel like I hated physics in school, can you raise your hand? And you're still here. That's amazing. That's really nice. No, that doesn't count. Okay, very good. Mixed. Well, so I know this is a Studium Generale, so I'm trying, I'll try to kind of take all of you along with, I hope, a kind of gentle introduction to nuclear fusion, and then I'll get really deep into what I do, and it's going to get really, really detailed. So I hope you'll bear with me till the end. If not, totally okay too. If you have questions, please ask them. I think the idea is like more towards the end and not in the middle. Yep. So let's do that. And then, let's get started. And let's try to, okay, I'll try to figure out how that goes. Where's my slides? Oh, there we go. Whew. Very good. Okay, so, cleverly shaped stellarators. Especially the last word, I'm guessing most of you don't know. I do hope that some of you have heard of the ITER tokamak in the south of France. Again, show of hands, please. Who? Oh, so many. Oh God, you'll be bored the first 20 minutes. Okay, all right. Cool, very good. Well, so the idea is really that we're making nuclear fusion happen on Earth. So why do we think that's such a good idea? Well, we've looked to the sun, which is a intimidatingly efficient fusion reactor, really, where a fusion reaction is taking place. It's a proton-proton fusion. The process is shown on the side. Oh, it's a very tiny pointer, but can you see it? Kind of? Okay, good. So where two protons are through several steps fusing to helium. This is working very well. The sun is shining, the sun is producing energy. Thanks to it, we're all here. It works really well because we have this so-called plasma state, so where the electrons are fully removed from the core, so that the cores, in this case the protons, really can fuse together. This only works if we have sufficiently high temperatures, otherwise the electrons wouldn't be removed from the cores fully. In the sun, approximately 15 million Kelvin, and at a very high pressure. Right? You can imagine, technically, we always have this big issue. If we have our electrons stripped from the cores, we have positively charged protons. And now we somehow want to bring them together in this fusion reaction, melting them together. It's really just kind of gluing them together. But they're all positively charged, right? So you might remember Coulomb force, very repulsive, only getting worse the closer the particles get. Technically, it's diverging, so if that was the whole story, we would never get to fusion. We could never bring these particles together. Luckily, we have the strong force, which is really at very small scales attracting our particles. So we're doing something very cool in quantum, which is something that I never really liked. And we're using tunneling, so the particles can actually overcome this repulsive force of the Coulomb force and be attracted to each other and therefore be glued together. Now, to kind of get to these kind of length scales where the strong force is in effect, we need the particles to be already really close together. And that works very well if the particles are either super fast and therefore just kind of, like running towards each other, or if there's really high pressure, right? You can imagine then the particles are just really close together. And the high pressure is really what works very well in the sun. We have the gravitational force pushing everything together. So in the sun it works really well. But how would we do that on Earth? I mean, we can't recreate the gravitational force here on Earth, right? There's no way. So let's first of all have a look at what kind of fusion reaction we're using, because the proton-proton fusion that's happening in the sun, I mean, it works for the sun, but it's also one of the harder fusion reactions. I mean, fusion in general is never really super easy. It's always, a matter of probability. So, like the particles, if they do fly past each other, they also kind of need to be feeling it, and usually they don't. So we here on Earth, people have kind of been dreaming of nuclear fusion for, decades, several decades. It's quite embarrassing almost. But it is really hard, so they chose the reaction that, even though it's still super hard, but it's the easiest to do. It has the highest probability of success, and that is the reaction of deuterium and tritium. So both are isotopes of hydrogen, one with like one additional neutron, another with two additional neutrons. Deuterium is actually existing in seawater. It's like also called heavy water. So it's really like existing kind of quite freely. You kind of just need to extract it. Tritium is a bit of a different story. It's radioactive with a half-time of 12 years. So if there ever was tritium on Earth, it's now decayed and gone, but we can breed it. I'll come to that in a second. These two then fuse and have this kind of unstable meta state here, and then they break off again into helium and a neutron. And if you kind of just count, like the particles are basically like the number of particles are still the same, but the mass of our two end products is slightly lower than the mass of deuterium and tritium, and this difference in mass is being transformed into energy according to Einstein's famous E equals mc squared. And the majority of the energy is taken by the neutron. This has to do with energy and momentum conservation. It's quite beautiful basic physics. It's really quite neat. So this is really the bit that we want to harvest, this energy. So if we somehow, it's in the form of kinetic energy of the neutron, so the neutron flies off really quickly. So we just somehow need to get the energy out, and then we're good. This is surprisingly like a fairly straightforward process. I'll come to that later. But really, how do we coax the deuterium and tritium into creating as many fusion reactions as possible? How do we do that on Earth? Oh yeah, sorry, first, I forgot this. The tritium, as I said, is radioactive, so it will be decaying. So what we always need to do is breed it here on Earth. We're using lithium, so it's kind of in your laptop battery. So some people have calculated if you took like a laptop battery and a bathtub full of seawater and extracted the deuterium and tritium from that, you could power up a typical family home for 30 years. So this is how efficient we're talking. And this is also why nuclear fusion is such a big dream. The energy contained in these cores, because this is energy at the core level, is really so high, right? Like compare this with you're burning coal, but really what you're doing is like some chemical reaction, right? It's like the energies in the electron sphere, basically. Is that sphere? You know what I mean, right? Like the electrons around the atom. So the energies that are associated with kind of reactions happening at the core are so much higher. This is why this is so efficient. All right, so we've already understood, okay, we need ideally very high densities, right? This is very logical. Like the more particles we have, the more frequent the particles can kind of meet and fuse. I also told you already we need very high temperatures because the particles need to be really fast to overcome the Coulomb barrier. And then we need something that's kind of slightly obscure, which we always call the energy confinement time. So the idea is, let's imagine we're having a reaction like this, deuterium and tritium meeting and producing a helium and a neutron. Then this energy of the helium here, if we can somehow take this and heat our fuel to keep the high temperatures basically alive, right? Then we would get to a state where we have really ignition, where our fusion reaction is kind of keeping itself alive. This can, of course, only happen if we're not somehow losing the precious energy too fast, right? Imagine it's like you're kind of firing up the fireplace, but kind of the flames are continuously extinguishing. This is what's kind of meant by this confinement time, keeping everything together so that it stays hot long enough. And there's various ways to do this. Really two realistic ways to do this on Earth. One of them is inertial confinement fusion. The idea there is that we're taking small frozen pellets of our deuterium and tritium, we're coating them, and then we're putting them into a little golden cylinder, and then we're shooting the little golden cylinder with huge lasers. There we're compressing it, so like the lasers are kind of bouncing off the walls of the golden cylinder, compressing the little sphere to super high densities, and then fusion happens. This works. It has been achieved, so I don't know whether you kind of saw it in the news. There's a big lab in the US where they have achieved it. However, shooting these lasers, and it's really like 50 lasers at the same time that need to be exactly in the same phase, is really quite challenging. So it's not really a thing that you would want to do as a reactor. Imagine you kind of have to kind of quickly replace the little frozen pellet in the little gold cylinder like every 10 milliseconds or so. It's cool from a physics point of view. It's really interesting physics happening there. I don't quite see this for a reactor. The alternative that I'm working on is magnetic confinement fusion. And here we're making use of the fact that our particles are charged. And as charged particles, they can be influenced by electric fields, but also by magnetic fields. And I don't know whether you remember, but we have like this famous three-hand rule, which I'm always kind of breaking my fingers with it. If we're having a particle kind of floating or like flying in the thumb direction, and I'm really hoping I'm not getting this wrong now because I haven't done this in a while, and then we're having a magnetic field in the kind of pointy finger direction, then the force the particle feels is in the middle finger direction. And I think you guys have like maybe like I've heard some people also kind of do something like this, and I never got it. But like I'm doing this. So if we're having magnetic field lines going through space, then this means that particles that are somehow kind of flying in some other direction, the direction along the magnetic field lines will be the same, so it'll just kind of keep flying unperturbed, but the perpendicular movement of our particle, perpendicular to the magnetic field, will be turned into a circular movement. So this means that our particles are really following the field lines in helical motions. And if you now think, okay, we'll have like lots of magnetic field lines, you can put like walls of our material left and right of it, and our particles would never touch the walls. And this is really important. Remember, I told you we need really high temperatures. In the sun, we have 50 million degrees, 50 million Kelvin. I don't know any material that would be happy with that. So we really need to keep our particles away from the walls, on the one hand to protect the walls, but also to protect our particles, right? Because if they hit the wall, they're cold, and then we can't have fusion. So this is one way of keeping them away. And the first idea was to just make a straight magnetic field. It's really easy to create, but then you have this issue, well, what if they hit the end plates, right? Then all the work that we've done is for nothing. And this is how people came up with this idea to twist it into a torus. This gets rid of the problem with the end losses, right? Our particles are now moving on field lines that are here in a toroidal direction. But there is a problem. I don't know whether you've ever played with like a little kind of racing car, right? Like with a track that you build in your living room. If the car is like in the corners and you are too fast, then it'll just, right, and off it goes. And that's kind of what happens to our particles as well. The particle feels the curvature of the magnetic field lines and just drifts outwards. And what you can do instead is that you create a twist in your magnetic field lines, and then the particle, which is maybe out here, will be then, thanks to the twist, be transported inwards again, and therefore nothing bad happens. Our particle stays inside, stays in the plasma. And this is what we're doing. There is two big ways to create this twisted magnetic field. One of the most famous ones is the tokamak, which is also the ITER in the south of France. And so here we're seeing our plasma in purple, we're seeing our twisted magnetic field in green. This is exactly kind of what we want. And there's two ingredients to build this twisted magnetic field. On the one hand, we're using magnetic field coils that are shown here in copper, and the magnetic field coils, like these D-shaped ones here, they're creating the field that is shown here in yellow. So they're creating a field in the toroidal direction, or the donut direction, if you will. And then we're creating a current in our plasma, which is shown here in red. And the current, and now we're using another lovely hand rule, if we're having a current in the thumb direction, that creates a magnetic field in the direction of the fingers of the right hand. So we're creating an additional field that is shown here in blue, and together these two magnetic fields just add up together. They'll give us this green twisted magnetic field. Now this is really quite nice. The magnetic field coils all look alike. We have this beautiful symmetry, and the physicists among you might remember Noether's theorem, which kind of comes with some conservation properties, really beautiful stuff. We'll come to that in a minute again. But having a current, like that's clearly necessary, right, for the twist of the magnetic field. But how do we get a current if there's no plasma in? But how do we get the plasma in if there's no twist yet? So it's a bit of a chicken and egg problem, and it's really a bit of an issue. How do you start up the tokamak? Also, it is a bit of an issue because the plasma is creating its own cage, right? So imagine the plasma just moves a tiny bit upwards because some disturbance, I don't know, like a big car passed by the lab or something, right? Just like the plasma just moves, like for some weird reason, it can be like a tiny movement. Then it's taking part of its cage with it. There's nothing that's stopping it from going even further. And in fact, there can be some like really dangerous positive feedback loops that just make the plasma move up even further. And these are so-called current-driven instabilities. So this is really something that you'd want to avoid if you build a big reactor that is expensive and that's supposed to run for 30 years. Nevertheless, tokamaks did really well because of Noether's theorem. They really had like some really nice results. The first really good results came from Russia, and then all over kind of the US and also Europe, people switched to this tokamak concept, and now we have some of the most successful experiments in the world being of the tokamak shape. So for example, we have the jet. Ooh, where's my pointer? Okay, my pointer's dead, I think. Yeah, it's dead. We have the jet tokamak, which is shown with like the beautiful 1970s orange coils. And then we have the ITER tokamak on the far right, which is really the biggest tokamak that is currently under construction. And I'll be talking a bit more about that because it's such a big and important experiment. If we would cut all of the donuts at like the same spot, they would all look really similar. And the fact is, it has been tried and tested that like that shape works really well. You can imagine, right? Like it's a very specific shape, right? You would ask, why not make it rounder? Why not make it even thinner or something? People have experimented with that, and this shape has really just worked very well. There is some freedom there, but for ITER, people were like, no, let's stick with what we know, where we have experience. Let me go briefly back. The reason why ITER is so very big, you can understand if we're going back to this idea of the energy confinement time, right? Like this idea that we need to somehow keep our energy in our plasma. And it's a bit like, I'm sure you've experienced this, like a foot bath is cooling down much faster than the bathtub full of water, right? Just because of the sheer size. And this has to do with like the difference in surface to volume ratio. So if we're having some sort of heat loss mechanism, so just, like, I don't know, the heat kind of leaving through the water surface in like our foot bath analogy, then kind of just making something bigger, having a bigger volume, a better surface to volume ratio, it just cools down slower, so this will kind of get us closer to ignition where our plasma is self-sustaining. This is why ITER is so big. So it's not particularly elegant physics, but it's been calculated that just making it bigger will work. So let's come to ITER. ITER's mission is really to show that we can build a fusion reactor, or it is still an experiment, it will not produce energy, where we have a burning plasma, which is self-sustained. As I said, right, we want to have this energy from our helium being fed back into the rest of the fuel and keep it warm. The idea is that we're using 50 megawatts of input heating power and having 500 megawatts of output heating power. Again, we're not going to power the south of France, but we can calculate, we'll have fusion reactions happening so often that this amount of energy is being produced. And if we were to extract it, then this would be the amount. It's a huge multinational project. So there's really the majority of the world population are contributing to this experiment, which I think is a really great feat, also in terms of world peace and stuff. And it's really the biggest experiment in that sense, politically speaking as well. So this was really decided between Reagan and Gorbachev to build this big experiment. There was a huge discussion where to build it. It was between France and Japan. In the end, people settled on France. And construction began in 2007. Well, the real construction in 2010. People are still constructing it, so it's a lengthy process. And one could maybe do this faster, but I'll come to that in a second, why it is so hard. So here we're seeing a drawing of this big experiment that it's supposed to be. And here in the middle, you might recognize, like the glowing pink thing, that's the plasma. That's where kind of the exciting physics happens. All around it is just pure magic of engineering. And here you can see also why it's taking so long, right? Just kind of imagining building something as big, as intricate for the very first time, and then with so many countries wanting a piece of the knowledge. So we have really several world firsts. We have this huge magnetic cage. We have here in the middle the solenoid, which is creating the current in our plasma. So it's by kind of inductance, 13 meters high. We have these big magnetic field coils, which are creating the field in the toroidal direction, in the donut direction, 17 meters high. We have additional magnetic field coils that are basically on top and below our plasma, which are so big, right? Like they're up to 24 meters in diameter. they're so big you can't even build them somewhere else and then ship them, because how would you transport something that's 24 meters wide? So you had to build a coil winding facility in the south of France to make them like right next door. Then we have superconducting magnets. If we're creating magnetic fields that we need the magnetic field to be really high to improve how well our plasma kind of keeps the heat. This would not work with copper because it would kind of heat up too much and then we would lose all the energy. So we're using superconducting materials, which in this sheer amount also, so like this is all the superconducting material that we're seeing here. It's really 10,000 tons of magnet material. To have our superconducting material being actually superconducting, we needed to cool it almost to absolute zero. So we need liquid helium, 25 tons of it circulating in the ITER tokamak. In general, we're talking huge construction size. So here we're having a little human, and here we're having just a tiny bit of one of the coils. So you can see it's really, naval construction size. At the same time, we need ultra high precision because, it's all been calculated to kind of work exactly like that. If it's off, if the symmetry isn't there, Noether's theorem, goes out the window. So we need to be super precise as well, while having these huge construction sizes. In comes the beauty of politics, which I'm saying this so sarcastically. I do think it is really an immense feat, because of course, in the end, fusion is supposed to be there, for all of humanity, right? Like we don't want to build something and just make a few people rich. So the idea of ITER is also to create knowledge, but make it accessible to everyone, that everyone has the knowledge right away. So it was agreed upon that many of the components wouldn't be, you could have been like, okay, US, please, you make all the coils, and EU, you make, I don't know, the vacuum vessel or something. But no, it was really divided into parts so that more countries would benefit from the knowledge at the same time. This also means that if someone learned like, ooh, this way of making the magnetic field coils, not such a good idea, it's very likely that another country made the same mistake as well. So this leads to quite some problems. Also, like the coils themselves, right? If you just have a look, gone again. Like also the different parts, for example, of a coil were not all manufactured in one place. All of this leads naturally to some delays. So I'm sure you've read about this in the news as well, like, oh, the ITER tokamak delayed again. It is disappointing also for me as a scientist, but it is also somehow understandable. It is a huge engineering feat with just so many players involved. Now we are on a fairly good track. So here we're seeing the construction site from a few years ago. On the left side, we kind of see like the white and red crane and like this round thing in the middle. This is where the actual tokamak will go. In the back, like with the red stripe on top of it. Oh yeah, my light is going again. This is the place that I told you about, where these big coils that are kind of on top and at the bottom of our tokamak are wound in place. So like really, like this is the place where our fusion experiment will stand. Everything around it is auxiliary stuff that is needed to run our experiment. And this is being built at the same time. This was the progress, or like the status a few years, like 1 year ago, I think. So this is, don't see it anymore, but this is where the tokamak is inside. So really some quite nice progress, but it will still take a couple of years till actually the first plasma can be switched on. So here we're seeing, so this was May 2022, so really, almost exactly 1 year ago, the first coil and the first vacuum segment was put into place. So good progress, but still needs a while. In the meantime, the jet tokamak, so the predecessor, like one level smaller than ITER, had a new record in nuclear fusion. The last one had been in 1997, and people were getting a bit impatient, like, where's the exciting physics? Why aren't we making progress? This has mainly to do with the exciting physics, or like the records, right, in terms of, oh, we're producing that amount of energy, only happens if you're actually allowing this reaction of deuterium and tritium to happen, right? If you're only putting deuterium and deuterium in, the plasma does its thing and you can study the physics, but no fusion reactions are actually happening because they're super unlikely. So you always need to wait until you want to use tritium. Tritium being radioactive makes the handling, makes the experiments all a bit messy. So unless you're really going for some, press-worthy material, you probably stick to deuterium. But in JET they did, so they used the deuterium and tritium. They achieved a new record in fusion energy, which, new records are always nice. The really amazing thing, though, was that the theorists, and I'm a theorist, so this makes me kind of happy, predicted exactly how this would go. They had models, they calculated in advance. They said, okay, this is the amount of heating you need to put in. This is exactly when you need to add some more fuel. And they predicted exactly the plasma behavior as it happened. And this is already nice, right? Like this, for a theorist, that's already pretty amazing. But also the same theories, which have now basically been proven to be right, they also say that ITER will actually work as planned. And you would say, like, well, you would hope so. You're building this expensive machine. But quite frankly, right? I mean, ITER, as I said, was built on this idea of let's make it bigger. And of course, there were clever physicists expecting this. But you can never be sure. Something as big hadn't been built, hadn't been run. But now we have these models that are really much more advanced, and they say ITER will actually reach ignition. And this is really good news for the entire community. Now, so let's assume ITER works, and we can show, okay, we can create a burning plasma. Then what's next? Why isn't ITER a reactor yet? What would we need for that? Well, we have this fusion reaction, right? I told you, and that the actual thing that we want is the energy of the neutron. Now, I told you the neutron is, well, or maybe a neutron is neutral, as the name says. So it really doesn't care at all about the magnetic cage. So we have this very fast flying neutron just escaping our magnetic field. This is actually a good thing, because now we can let it hit the walls. And this sounds like a really terrible idea, but it's really what gets us the energy. Because the idea is that we're letting our neutrons, with lots of kinetic energy, hit our walls. In the wall, they're stopped, right? Like imagine like a bullet being stopped by a concrete wall. You're shooting at the wall, and it's not passing through, ideally. In this process of being stopped by the concrete wall, or like in our case, by the metal wall, the kinetic energy is transferred into heat. So our neutrons are basically hitting the wall, heating up the wall by being stopped. And then all we need to do is we let water drizzle over our hot metal wall, and the water is being heated up to steam, and then we have a steam turbine, like the classic way, basically like a coal power plant, just cleaner. And there we go, then we have energy. So in a sense, it's a very fancy way to make steam, which, there is room for improvement. So like if we'd use a different fusion reaction, this could be more elegant. But for now, this is what we got. And I mean, at least this is the part we know works, right? Making steam and making energy from it, we've been doing that for centuries. So that's the good news. So, yeah, we could put a tokamak in there. We could make ITER even bigger and then have a fusion reactor. And this is really what we're trying to prepare with ITER, right? So we're learning about ITER as a tokamak, how it works, what the physics is, how the plasma behaves in it. We're also learning a lot about the technology. What do we need to do to make our magnetic field coils very stable? How do we produce them efficiently, and so on? And then we could, scale it up and make a reactor. But this is the exciting bit, because this is like where my research comes in. We could also take a different shape, namely a stellarator. And this is something that is also being currently explored with the Wendelstein 7X experiment, so W7X here. So let me tell you about that and why I think it might actually be better than ITER. Well, okay. So I've told you all about tokamaks, right? I've told you we're creating this magnetic field, this twisted field with the coils and a current in the plasma. And I've also told you that there's issues with having a current. Okay. Namely, these problems are these current-driven instabilities, and I didn't even tell you about that yet, the pulse operation, right? How do we get a current in the plasma? Well, with a transformer in the middle. Well, but the transformer action only works by switching it on or switching it off. So like naturally by having this, by needing this current in the plasma, this can always only be a pulse operation, which is not ideal, right? Think of like the stresses and the changes in stress on our materials. In comes the idea of a stellarator, and it kind of sounds a bit like this was like an innovation, like that came later than the tokamak. It really isn't the case. Like they were basically invented at the same time. And the idea of the stellarator, it's really deceptively simple. It's like, well, let's just create the entire field by magnetic field coils. Just like not have a current, but just, you know, add a bit other weird coils and create the magnetic field with that. So you see here, we have the coils, basically like the same ones that are going around the torus as in the tokamak. But in addition, we also have these helical coils here. And together they create this twisted magnetic field here shown in green. Now, the idea was kind of nice by Lyman Spitzer, a famous astrophysicist, allegedly while he was skiing, and the ski lifts were really slow back then, so he had lots of time to think. That's when he came up with this. Now the tragic comes in. You can show this mathematically, that if you don't have a current, you can't make the device symmetric like this. It's just like, yeah, you just can't make it symmetric. This means Newton's theorem goes out the window, and this means that our particles are actually less well confined, and I'll show figures of that later. So because of this lack of symmetry, our particles are leaving the plasma, which is exactly what we didn't want, right? Like this is why we built this magnetic field in the first place, because we wanted our particles to stay inside. The good things are, okay, we could now have continuous operation and wouldn't have any instabilities, but well, if our plasma is cooling down too fast, you know, we might as well just like stop this. And this is literally what happened. People were experimenting with tokamaks, they did really well. People were experimenting with stellarators, they did really poorly. Well, then what do you work with, right? You work with tokamaks. And this is basically what's happening. So here we're seeing the magnetic field strength of a stellarator in, like a normal one, basically. And we're having like this toroidal shape. And then you're seeing, you can imagine, just let me go back one slide. If the coils are closer together, right, the magnetic field will be stronger there, right? That's very logical. What is also logical is that the magnetic field will be stronger where you're really close to these helical coils here. And this is basically what we're seeing here. Here we're having like the magnetic field being very strong because there's a helical field coil very close. And in general, the magnetic field, like red is higher magnetic field, blue is lower magnetic field. Generally, the field is higher on the inside and lower on the outside. Now, you might know this from energetic particles hitting the Earth's magnetosphere. Charged particles are being reflected when the magnetic field gets too high, right? Like in the Earth's magnetosphere, they're kind of hitting the Earth, like coming from the solar wind, and then at the poles, the magnetic field is getting too high, so they're being stopped, being reflected, and that's what's creating the aurora. Something very similar is happening in a fusion device. First, let's have a look at the ones that are not reflected. So this happens when the parallel velocity, so like the velocity along the magnetic field lines, is high enough. Then our particle would just follow the magnetic field line. And what I'm not showing here is, of course, like the helical motion is still happening, right? But it's very small, so I'm not showing it. Let's go back to the particles that are being reflected, like the energetic particles in the Earth's magnetosphere. These particles will basically be reflected as soon as the magnetic field gets too high. So let's imagine we're having a particle which is starting here in this region of low magnetic field, and then it's following a field line, and then it's like, oh, the magnetic field is getting too high, it's being reflected, and then it's going back. And now what you can maybe imagine is it's only seeing the curvature of the field line in this region, right? It's a bit as if you're forcing your little racing car to stay in the awful curve where it's kind of leaving out. And this is what this particle is feeling. It's constantly being forced to stay in this curve and therefore being forced to drift out. The particles here, the ones that are not reflected, are also spending some time in the awful curves, but they're also kind of being transported, into the safe region. So like these particles don't actually leave our plasma, whereas these particles do. And this is really the reason why stellarators performed so poorly, because of this lack of symmetry. This is really not the case in tokamaks. So here we're seeing also the magnetic field strength of a tokamak, the region of low magnetic field is shown in blue. We're seeing the trajectory of one of these particles, and you also see it's also reflected in the region of higher magnetic field. And it's also drifting somewhat, so it is feeling some sort of drift, but the drift is not actually outside of the plasma, but more within the surface, and that's totally fine, right? Like, let it drift. Like, no, that's not dangerous. That's not going to make our plasma extinguish. And here we have like our stellarator plasma that I already showed, where our particle is drifting. Now, luckily, in comes theory to the rescue. We can trick the particle into thinking that it's in a symmetric field by creating something that is called quasi-symmetry. And it's really quite elegant. The thing is, if you write down the equation, and now I know I'm geeking out slightly, but it is so pretty. If you write down the equation of motion that the particle feels, you can actually show that in a decent approximation, the equation only depends on the strength of the magnetic field. Usually the magnetic field is a vector, but in lowest order, in a decent approximation, only the strength appears. And what you can do is you can make the strength of the magnetic field be only dependent on two variables, and they can be super weird variables, right? So there's, you might know Cartesian coordinates, x, y, z, kind of perpendicular to each other, right? Like that's the usual thing that we do. You can also create something that's called curvilinear coordinates, and it's really, you just kind of come up with like some weird way to describe the location in space. And if you, for example, have a look at this one here, you see that the magnetic field strength here along this helical curve is actually not varying, right? So if you were to define a variable that would always sit here in this minimum, then your magnetic field strength will be constant along that coordinate. And that would be a good coordinate in this case. And this means that our particle is actually thinking it's in a tokamak field, and therefore not drifting radially outwards. So here we're seeing a particle in this magnetic field, and you're seeing it's also drifting within the surface, like in the tokamak, but not drifting radially outwards. And this is exactly what saved stellarators. There's different ways to do this. So here, this is how Wendelstein 7X did it, and we're also seeing the particle being reflected, but also not drifting radially outwards. Now, all of a sudden, thanks to this so-called quasi-symmetry, stellarators actually are as good as tokamaks. So we have all of a sudden this good confinement thanks to this quasi-symmetry. Now, I don't want to bash tokamaks too much, even though it's something I love to do. Because, of course, tokamaks have evolved as well, right? There is now ways to do continuous operation. You can do clever ways of doing current drive that do not rely on the transformer in the middle. And what is also really neat, actually, and where we needed a lot of help from, for example, mechanical engineering, is that we can actually control instabilities, right? You can constantly measure your plasma and just do something about it, right? Like, you now have self-driving cars that are not kind of driving off the street. You can do the same, basically, with a fusion reactor. Now, the neat thing comes in. You might think that this loss of symmetry in stellarators is a bad thing, right? Like, because the particles are not confined. But once you are liberated from this thing that is symmetry, where everything kind of looks the same, you can get really creative with the shape. And here we're just seeing a very small selection of shapes that have been thought up of stellarators. And actually, people have said there's about 40 shape parameters that determine how the magnetic field looks like. And if you were to say, like, every one of these shape parameters, you would have like a scale of you would have like 10 different steps from like very little of this parameter to very much, and then you'd do a combination of all the possibilities. You'd end up with 10 to the 40 possibilities of plasma shapes. That's more than stars in the universe. Visible stars. Who knows? So really, there's a lot of freedom there. And now the only question is, which one is good, right? I mean, and definitely not all are equally good, right? We've already seen like this old version, that was definitely not good. You do not want to go there anymore. So what do, right? As physicists, we're like, okay, we have so much choice. We now need to pick a good one to build a reactor from. Well, this is, let's call this our shape cloud. So kind of these are just like a selection of possibilities that we have. These are kind of representing the different shapes that we have. And now we can put them into big optimization codes. So usually is what we do, we're kind of picking out one shape. And for this one particular shape, we can calculate, for example, what are the particle drifts doing? Are they doing decent things? Are they like not drifting radially outwards? Do we have some evil instabilities? And this is actually, and then we ask which shape performs best. And this is, for example, how Wendelstein 7x was designed. So let's come briefly to Wendelstein 7x, because it is really the most advanced stellarator currently in operation. And here we have the plasma shape. It's a bit faint, I'm sorry, but you already see it's a really weird shape, right? Like gone are the donut-like shapes. It's like a weird, twisted, almost like Möbius strip, but not quite shape. It's created by really weirdly twisted coils, 50 of them, all of them superconducting, which also, coming back to the ITER, like clockwork precision, the same precision was necessary, and it was achieved actually. So, like humankind can do this. On top of that, we have some kind of boring coils because, we're still experimentalists. We kind of want to learn stuff, right? We don't want to kind of switch it on and be like, oh, so sad, that didn't work so well. So we have some freedom here. Then, of course, we also need to cool this entire thing. We put a vacuum vessel around it, and then it's closed off like this. Looks a bit like a spaceship. Someone wrote an article about it and kind of called it like Han Solo's Millennium Falcon after a really bad crash. So yeah, this is what we're dealing with. Here we're seeing some pictures in action. There's a really nice YouTube video which I kind of wanted to show, but then I was kind of too scared that it wouldn't work. So if you're ever bored, Google it, Construction Zeitraffer, like in German, of Wendelstein 7x. It's really beautiful. You kind of see it in action. But yeah, let me briefly go back. It's maybe faintly visible, but Wendelstein 7x is actually like a pentagon. And if you take each of these fifths and you cut it in half, then you get a so-called half module, which are kind of constructed separately. So here we're seeing like one fifth of the entire thing, kind of two of these half modules put together. You're seeing the weird twisted coils in silver. You're seeing in copper the kind of the slightly more boring planar coils for experimental flexibility. Then the entire thing is kind of taken by one big crane. Fun fact, they kind of built it and the crane was too weak, so they had to build another crane. And it's kind of being floated into the hull. In the hull, you first put the outer part of the vessel in, and then you kind of very carefully kind of place the module in millimeter precision into it. Then you also need to kind of connect them, and you can imagine those are not clean cuts, so it's, yeah, it was quite challenging. The welders also were kind of some of the highest paid people because you needed very good welders so that not everything would fall apart. So here, this is basically everything is in place except for the shell on top of this very final module. And yeah, and this is how it looks like now. Lots of cables, kind of all these holes here. They would not be there in a reactor. These are really there because it's an experiment and we still want to learn about the plasma. So these are lots of holes peeking into the shell to have diagnostics and to observe the plasma. What is it doing? The heating goes in, and so on. There's also some slightly bigger ones where a human can crawl in. It's not great. You need to be fairly small for it. But yeah, it works. Then in 2015, Angela Merkel came and switched on. Of course, this is a fake button. We would never allow her to switch it on properly. Also, we might have tried it the day before, so she wasn't actually there. But yeah, so that was a pretty big deal, switching it on. And the nice thing is it works. It does exactly what it promised to do. The particles are well confined. It's behaving really beautifully. You switch it on and it runs for like 8 minutes and you sit there and it looks really boring, which is a bit, from like Marvel movie spoiled person, maybe not so great. But this is what you want for a reactor, right? You want it to behave. Well, why aren't we just kind of taking Wendelstein 7X and making it a reactor? Well, there is this issue of turbulence, and now we're coming to my research topic, and I know we're like slightly behind time, so let's see how far we get before you fall asleep. Well, turbulence is really everywhere, right? And I've put here this little image of like the hot tea and the cold milk. I really hope that all of you are putting in the milk after the tea. I'm very, very strict about that one. Because if you do, then you see turbulence developing, right? We have this gradient in temperature. We have the hot tea, we have the cold milk. Admittedly, in this case, we also have differences in velocities. But yeah, turbulence develops, and it's really ubiquitous. It's everywhere. We have it in the Earth's atmosphere. You've all kind of witnessed it when being on a plane. So it's really nothing that can be avoided. As soon as there's differences in temperature or differences in density, there is free energy associated with these gradients. So the turbulence taps into that and takes it and turns it into basically kinetic energy. Now, of course, we have that in a fusion reactor too. I mean, I always told you that we have these 15 million degrees and we have like fairly dense plasmas. And sorry, I forgot to say that, but like with dense, we're still talking like several orders of magnitude thinner than the air. But that's still sufficient for fusion. But at the same time, what we are definitely sure of is that we don't want any heat at the boundary, right? So we want really out here, we have proper vacuum, we have no density whatsoever. And ideally, our plasma is really cold out there as well, because otherwise we'd be melting the wall. And so between like the 15 million Kelvin in the center and basically 0 Kelvin at the edge, we have like 2 meters. So these are insane temperature gradients, and the same holds for the density. So you can imagine turbulence is having a field day. And the bad thing is that the turbulence leads to heat loss. So imagine again, milk in the teacup, right, leads to mixing. So all of a sudden, our precious hot tea is also transported from the center of our teacup to the edge, where it's touching the cold, I don't know, ceramics, porcelain, whatever you want to use. And then it cools down much faster. This is exactly what's happening to our fusion plasma, and this is exactly what we don't want. So turbulence tends to not just appear. We need certain instabilities. And instabilities are really something, if we just have a small perturbation, and then it grows. And a very famous example is Tahoma Bridge in the United States, where, again, beautiful YouTube video. I really encourage you to watch it. I'm not including it here, but like it was like a bridge, and there was a strong wind once, and somehow it achieved that there was a resonance between the wind and the small movement of the bridge, and that got so big. So like this initial like very small swinging of the bridge got so big that the structure couldn't handle it anymore, and the bridge broke. And this is, instabilities in fusion plasmas don't look as drastic, but they're similarly undesirable. So here I've just painted a little picture. So we have here like the arrow is pointing inwards, like this is a density gradient. So it is getting like more dense in this direction of the arrow. So you could imagine in our fusion reactor, this would be radially inwards. So if we're having a small perturbation here, then whether or not this perturbation grows really heavily depends here on these particle drifts that I've pointed here, that I've drawn here on the at the bottom. And this heavily depends on the geometry of the magnetic field, and this is really where optimization comes in. And these drifts are exactly these drifts that we've already seen that were associated with the particles being trapped or being reflected in the magnetic field. So of course, there is one way of just kind of killing it all. We could just use very fancy computer codes, right? We could just take our shapes of our stellarators and ask, which of these shapes is actually doing well enough, and just kind of compute the whole thing. And the reason why we might want to do that is that the simulations that we have already done have shown that the turbulence does look very different in the different shapes, right? And here we're just seeing the fluctuation level, so really how turbulent are things. And where it's red, this is where the turbulence is really strong. This is in Venetian 7X, and these are two other stellarators here. And the calculations have shown really that the amount of heat that is lost in these different shapes is really very different. So really there is hope. The only question is, okay, which shape do we want to build in the future that has kind of the least amount of turbulence? So we could go back to our fancy code where we're doing this optimization that we've already used to calculate Venetian 7X and just include turbulence within our optimization loop, right? Like for each of these shapes, ask again, how bad is the turbulence? And if we're then taking a small step to like a different shape, and if it's getting better overall, then we might continue changing our shape in that direction. And if it's getting worse, then we're kind of turning around and trying a different shape, right? That's how optimization usually works. Now, including turbulence would be necessary for a reactor. And we could do this, we could just use our fancy codes that we have that I've shown you the pictures of. But each of these simulations, we're talking 5 million CPU hours. So, you know, your typical laptop has maybe 4 cores, maybe if you're being fancy, 8. So you can calculate how many hours your laptop would need to run to calculate only a single one of these shapes. And remember, we had 10 to the 40 possible shapes. So this is really not an option. So what we need is some physics understanding of where these instabilities come from. And I'm already seeing Vedan getting a bit impatient. Okay, then, oh yeah, that didn't work anyway. All right. Okay, then let me think. Okay, so, Okay, so what we have done is we've taken different shapes, right? Like the Venetian 7X stellarator, you maybe already know. Let me go back to this picture here. This is how Venetian 7X looks. And you've also maybe remember the helically symmetric stellarator, where I kind of explained to you this idea of quasi-symmetry. Well, if we do simulations and we're asking what is this, like one of these instabilities, how bad are they? And we're measuring how fast they're growing. Then we could make a plot like this. Here at the bottom we have the density gradient. Here we have how fast our evil instability is growing. And we're seeing the HSX stellarator is much worse than Venetian 7X. And we can explain this based on this whole idea of the geometry influences so much whether or not our instability is growing. A bit like if we had built a different bridge, Tahoma Bridge might have not collapsed. So the idea is, can we make the HSX stellarator a bit more like Venetian 7X, right? And we have these currents in the coils that are creating the magnetic field. So it should be possible to tweak the coil currents a bit and make it better. And this is what I tried to do. That's already a few years ago. And this is what I came up with. I mean, so like this is like a measure of how bad the turbulence is. We call it the heat flux. This, so kind of the higher it is, the worse it is. The red line is our initial, like the actual experiments that's in the US. And the blue line is the one I came up with. Okay, cool. I reduced turbulence by a factor of 2, not bad. But let me briefly go back and let's have a look at the shape here. This is really very ugly, right? We've lost completely this beautiful quasi-symmetry. So actually, in this case, even though the turbulence is less, our particles would, you know, be running off again. So it is really like optimization is really an art. You have to know what can you sacrifice for the thing you want to gain. And yeah, maybe, oh no, one last thing, and then I'll stop, I promise. This thing that kind of this heat flux, the fact that this heat flux was really much lower was actually a really lucky coincidence. Because in fact, this whole idea was really only based on this idea of, oh, we understand what our linear instabilities are doing. But like one instability, right, like imagine like this initial perturbation is just growing. That's not the only thing that's happening. There's lots of these small perturbations growing at the same time at different speeds. Basically, at some point they get so big that they're influencing each other. And this is when really kind of nonlinear physics kicks in. So like, yeah, when you can't just treat these instabilities separately anymore. And then something really weird happens. namely the HSX stellarator that was here linearly, like just which instability is growing fastest, is really not doing great. But here, if we're looking really at the nonlinear physics, the full turbulence, they're basically the same, right? So somehow the instabilities are interacting much more violently in Wendelstein 7X than in HSX. And this is something that we're literally only now starting to understand. And yeah, I'm not sure whether this is makes me feel better, but I mean, fluid turbulence is similarly not understood yet, and that's, I mean, even Da Vinci started working on that. So I do hope we're faster than that, yeah. So yeah, this is what I'm working on, and maybe like for a long time, so I have a job for a long time, but on the other hand, also, we do want to have fusion working soon. Sorry, I'm just skipping this. I'm sorry. Please ask me. This is, work by my PhD student. Lovely stuff. But yeah, in view of time. But yeah, so I hope I could convince you that nuclear fusion is an interesting subject and that it might be a really nice option for energy for the future. We have made some really amazing progress in the last decades, but really also years, right? Like the entire field of stellarator physics has really only been in the last few years. And I really think we're almost at a stage where we can start thinking about reactors. I'm personally, and I think I'm not alone in this, but I might be slightly biased, I do think it could be a stellarator, not a tokamak. And yeah, maybe we could start thinking about building it in the Netherlands, because why not? It could be in Rotterdam, and I think we should try for that. Okay, thank you so much.
And now it's off again. Okay. Thank you. That was a very nice talk, and it was very entertaining for sure. We have some room for questions. We have a microphone in the front here that hopefully someone will get by, otherwise I'd have to run around. But yes, if you have questions, please raise your hand. It'll be sort of one at a time. Please only ask the question if you have the microphone with you, and maybe not a lot of questions. We can start from there, from the back, maybe? Yeah? And then I'll sort of just move from the back to the front so we don't have to do a lot of running around the room.
You didn't mention it.
Sorry,
is it no longer a problem?
The what?
First wall problem. The wall is bombarded with helium. It makes clusters and blisters, and it's the end of the first wall.
Indeed. Yeah, I glossed over that. So, okay. Maybe for the rest of the audience, indeed, right, like if you imagine that our metal wall, right, if everything's going well, our particles are technically not hitting it, right? If our magnetic field cage is done well, then they're not hitting it. But neutrons are hitting it. And of course, once in a while, even our particles, even our magnetic field cage isn't perfect, so still hot particles might hit it. This is bad in various ways. This could be like really lead to atomic changes, but also just like very hot particles hitting metal. You can imagine it's not a pretty sight. There is some very interesting research being done, also in Eindhoven, which kind of makes me slightly proud. So people are experimenting, for example, with liquid metals. So kind of this idea is that you have liquid lithium, for example, floating over the walls. And then, because it's a liquid, right, like even if like a particle, say like a neutron is hitting it and like splashing something away, the liquid layer would close again, so it's basically self-healing, it's also replenishing. I think in practice we'll still need to figure out how to make this not a really big mess. But I think there's hope. But it's not fully solved yet, yeah. Yeah, good point,
okay.
But sore point also.
More questions?
I think up there and here.
Yeah, here's also fine.
Yeah, okay.
I'm trying to keep it
You were the first.
maybe segmented to this side and then we move to
I
that
think
side
you have
because
a
that's
question
maybe
as well.
easier.
Yeah, okay, and then
Hi. I was just wondering, the fusion that's taking place or that has taken place in the US with the lasers. For what I understood, they were using really ancient equipment. Is there any hope for that project, in your professional opinion?
It's scientifically a really interesting experiment. Yeah. I think it would be really hard.
Yes, my question is about the basic reaction, where you have the helium atom that is escaping as the ashes, like a sort of byproduct. Is there any way of meaningful recovering that and use it again? Because you need a lot of helium for cooling stuff.
Yeah, indeed. So people are thinking about this. So the helium that is created in the reaction is still charged, so it's technically not escaping as the neutrons are. But there is a region where the magnetic field lines will be open, and it's called the diverter. It's a bit like the place where you take out the ash from like the oven. And there you can kind of suck out the plasma. Of course, you'd be also sucking out the deuterium and tritium, but there are ideas to recycle the helium through that. Kind of take it out and then put like deuterium and tritium back in, but not the helium, obviously. And yeah, there are thoughts of recycling that, because indeed the cooling of the superconducting coils is a big challenge. I do think there's a lot of potential with high temperature superconductors, because then of course you don't need helium, but only liquid nitrogen, as far as I know.
Okay, maybe one more question here before we move over to that side.
Okay.
And now I need to pick one of these two people. Maybe the person at the back can.
I'll also be here like for the drinks after, so you can always ask me
Yeah,
there.
there's also a chance to ask questions, further detailed questions afterwards. Indeed.
Hello. Yeah. Okay. Thank you very much for the talk. I'm very interested in nuclear fusion, and I was looking at this this picture, and there seems to be some sort of five-fold kind of symmetry in the shape of the in the W7X. I was wondering why that is, and why 5 and not 7 or.
Yeah, it could also be 6 or 7. I've asked this question so many times and have not gotten good answers. I'm sorry. It's like one of these quantities you can kind of choose fairly freely in your code. I mean, it is a bit, right, if you think you'd only have 3, right, then you'd basically have a triangle, and that would make your corners super sharp. And in terms of like this whole curvature, think of like the race car, that would probably not be something you'd want to do. But at the same time, having straight sections in between is really nice, because that's where you have no curvature, and curvature tends to be a bad thing. So like 4, 5, 6 is kind of the sweet spot. But there's no really good reason that anyone could tell me for like why 5. And really the reason why this is 5-fold again is just because they took Van 7X and they scaled it up. But it could have been 6-fold. It's just like an idea for like a reactor design. But yeah, good question. No, yeah.
Thank you. Yeah.
You're welcome.
Okay, now. Okay, that's a lot. Yeah, here's fine. He's been waiting a while. Yeah.
There is a risk of runaway reactions as well, correct? I noticed that in one of the diagrams there was what I assume to be beryllium coverings in green. Is that to reflect the neutrons back?
No, as far as I know, it's not. I think it's more of that it's a very sturdy material that can just kind of live with the neutron impact longer.
It acts as a neutron reflector, as far as I know.
Oh, it does? Oh, then you know more than I do. Yeah, I'm terrible at the material side. Sorry. But yeah, as far as I know, it's just very sturdy.
Okay.
Yeah.
I see.
But like in terms of runaway reactions like you'd think of like in a fission reaction, this is really not the case, right? Like in fission, you'd have like this really like the snowball effect of like neutrons being created, and then more and more you have this multiplication. And this is really not the case. You need like every single reaction is basically standing on its own. And the moment that the conditions aren't just at the sweet spot of temperature and density, then your fusion reactions are just quickly like not happening as frequently anymore. You won't have helium being produced, and therefore the heating extinguishes.
It's self-controlling, yeah.
It's really self-controlling. So like there have been experiment or calculations also, like like really drastic ones. Like what happens if, I don't know, like something crashes into the fusion reactor or something. It just like, yeah, there's basically nothing that would happen.
I understand, but I think I choose my words poorly. When I said runaway reactions, I meant literally running away from the reactor, the neutrons running away, from getting out of the reactor that we do not intend them to, when we don't intend them to.
Yeah.
But yeah, I understand. I just had some poor wording.
Okay,
I
right.
think,
Sorry.
yeah.
Thanks for
One
the
last
question, though.
question, maybe?
Question? You have
Yeah, maybe the photographer over there.
the other people on the drinks.
No, one very quick question. What is the order of magnitude of the fields that we're talking about?
So Venetian 7X has like 2.5 Teslas, but also like other designs, I think, are now talking up to 8 Teslas.
And ITER?
Oh God, no clue. I think 5 maybe, but ooh, I'm a theorist. I always normalize everything out. Sorry,
thank you.
I think 5. I think 5.
Okay, that was pretty quick, so we can do one more, I think. You were earlier, but you were very enthusiastic, so you can fight over the question.
Yeah, I know you don't like tokamaks, but I had a question about. I'm sure you've heard of.
It's okay. I'll take questions about that too.
Yeah, I'm sure you've heard of the STEP reactor in the UK that's being planned.
Yeah.
It is a different design.
It is.
That they have hope in. What are your thoughts on that?
So the STEP reactor that they're planning to build in the UK is a tokamak, so it still has a symmetry, but it's a chubby one. So, like if you're looking that there's like a big hole in the middle, the STEP is basically the opposite. Really think of like an apple where you have taken the core out. And it's, as far as tokamaks go, really one of the more beautiful designs. Because it comes with like quite a few advantages in terms of the curvature that we've mentioned and so on. It has really some problems as well because you don't have space in the middle. So there's basically no space for neutron shielding of like the central solenoid, which is not great, right? Like if you're having your precious magnet in the middle and it's bombarded by neutrons, not so great. I think they've claimed they have a solution to that, but they're not super transparent about it. But I think they've just decided to make it a tad bigger so that they have more space now. So like moving slightly away from like the total apple, the spherical tokamak, making it a tiny bit more conventional, but like not quite. It's decent, I think. Okay. It's not a stellarator. What do you expect me to say?
Okay, I think we're out of time for questions, but if you do have more questions, then you can ask downstairs when we go down for drinks.
Yeah,
I'm not
do.
sure exactly where that is, but I imagine there are signs, hopefully. Thank you all for being a very nice audience, and you've had some very nice questions. And thank you, Josefine, for a very, very nice talk. I have 2 gifts here for you. The first one is from Studium Generale. It's a book in Dutch.
Cool. I do speak some Dutch. It's just.
I think by the time you're done with the book,
much.
you'll have a very good understanding of Dutch once you're done. So,
okay.
Hopefully.
Thank you so much.
And then from us, that's the foundation. We have actually pretty nice stuff, Max. I haven't looked at it before right now, so I hope it's good. Here.
Thank you so much. I really appreciate it. And thank you so much for having me.
Yeah.
Thank you so much. I'm Anita de Waard, and I just want to thank the FMF De Waard Stichting. This was a really brilliant talk. I think my dad would say, you know, what do you need to have a great evening? You need great physics, you need a motivated, passionate speaker, and you need very good organization. And I guess the fourth thing would be drinks. So we're getting those in a second.
Yeah.
So thank you so very much. I think I learned more about fusion than I ever have, and I think the same is true for many people. So we've been both enlightened and entertained, and this was fantastic. And I just want to thank the Stichting De Waard very much for all their work. It's so amazing that this is still going. We were saying earlier, you know, what the BAFTA is to the Oscars, the De Waard is to the Nobel Prize. So this is a precursor of things to come. So thank you all for joining, and thank you so much.
Thank you. I have no idea where they are.
Okay. Thank you.
Yeah, so I imagine the doors are going to open and the drinks are indeed downstairs. Follow the signs, hopefully. Oh, that hurts.